the upper sum is greater than equal to lower sum. So what's next? How did they do the, how did they do the whole thing? So what they did is that they did an interesting idea. So observe that instead of selecting this xk and xk plus 1, they did the following thing. So one interesting thing they saw that, one interesting thing they saw, this is an observation. So I will not prove it, but observe this. They observe that, I will not prove it, okay? But they observe, you try to think why it is true, that as they made more finer, as they made more finer divisions of A comma B, as they made more finer divisions of A comma B, okay, the upper sum kept on decreasing. That is, as n is increasing, as the division is increasing, the upper sum kept on decreasing, and the lower sum keeps on increasing. Okay, as they made more and more finer divisions, this happened. The upper sum kept on decreasing and the lower sum kept on increasing. Okay. This was an observation. You can prove it mathematically. Actually, if you read Stephen Abbott, they have proved it mathematically. The upper sum kept on increasing. It's very easy to prove. You can prove it. Okay. The upper sum kept on increasing and the lower sum kept on increasing. And what they did is that they defined integration in the following manner. This is something interesting, so stay tuned. So since upper sums kept on increasing and lower sums kept on decreasing, they took all possible partitions. They took all possible 1,000 partitions, like all possible partitions. They took all possible partitions, all possible, x1, x2, xn, just two partitions, 3 partitions, 1,000 partitions, 1 lakh, 1 crore, all partitions, okay? And they define, since the upper sum kept on decreasing as the, so upper sum kept on decreasing, okay? And the lower sum kept on increasing. And certain point they will be equal, right? Understand this diagram. The upper sum kept on increasing and lower sum kept on decreasing as n increases, as n goes to infinity. So at some point they will be equal, and that point is actually defined as integration. So how they defined is, they took all possible partition, and the upper wala they took, since it's kept on decreasing, they took infimum of all un. Okay, the infimum of this u of f over all possible partitions of the domain. And here, since the lower sum kept on increasing, they took the supremum. Okay, and integration was defined as integration a to b fx dx is exists to L if and only if the supremum over all the lower sums, where p belongs to capital P, let's say, is equal to the infimum of the upper sums. What is P? P is a set of all partitions. Okay. If this happens, which is equal to L. If they have the same limit, it's equal to L, then we define this as this. This is the definition. You can see it's a pretty complex definition, right? A pretty complex definition, but it matches the integer. This is how our theory is built. It builds step by step, and I try to understand how to define it, and finally we get to define it. Okay. Okay, all of you understood the definition, guys? So we defined the area under the curve. We defined for every partition P, we defined the sum. We try to define the something close to the limit. For every partition, we try to define something close to the limit. We saw there are two parameters. One was the selection of the partition. Once the partition is fixed, this partition is fixed. So another was the selection of CI. Now, what to select the CI? They select the CI to the maximum and the minimum, the suprema and the infimum. So that fixes the CI aspect. Now there was a partition aspect. So for every partition, we got a lower sum and upper sum. And one observation was that if you make more finer divisions, the set of, the upper sum decreases and the lower sum increases. Just like this, the upper sum decreases and the lower sum increases. So for every partition, so we understand that we took, like, for every partition, we got a lower sum and upper sum. The upper sums are decreasing and lower sums are increasing. So at some point, they will be equal if it's integrable, okay? And how to define it? So they defined as, since the lower sums are increasing, so defined as the supremum of, they define something called the supremum of all the lower sums over the partitions. And since the upper sums are decreasing, they define the infimum, the minimum of all the upper sums over all the partitions. This will give two values. If the two values are equal, this makes sense. If two values are equal, they defined the integration to be that L. This was the definition of the integration, okay? This is how the whole thing is defined. But we will not do anything related to this. We will not do anything related to this. But this was how the whole thing was defined. I mean, mathematics evolved like, like a mother or parents raise a child, okay? It's like various aspects come into various aspects come, right? So it's evolved like a child, okay? It's like, it's not a linear process of thinking. Okay, it's like you think about something today and you think about some other thing tomorrow, and mathematics makes sure that they are coherent with each other. That's it. But it's not a linear way of thinking. So it's like, it's a very haphazard way of thinking. There are errors, but at the end, since they're trying to regress towards a coherent theory, so it regresses towards the mean towards the end, and there is a linear aspect overall. Okay, when you learn the books, when you see the books, the books are written in a linear way. So how to compute it easily, number one. Number two is that what type of functions are integrable. So if a function is integrable, if, like, this integration exists, okay, a function is integrable within this range, if the integration exists, okay, that's the idea. A function is integrable within this range if the integration exists. So that was the idea, okay? So how a function is integrable? What do you mean by integration? A function is integrable. A function is integrable if they are, that thing holds. What's next? So remember that. So this was the idea. Also, there is another thing. A function is called to be Riemann integrable. See, for the definition to exist, okay? Understand this very carefully. For the definition to exist, the supremum and the infimum must be there. Huh? So let's say there are a function like, shoots up to infinity somewhere and goes like this. So there is a small interval where the supremum will be infinity, right? But it can happen. It's totally fine. A function can be integrable because we are taking, after all, the infimum of all the supremums. Okay, we are taking the infimum of all the supremums. That's totally fine. But the idea is that we usually take the bounded function. Okay. So a bounded function are integrable. It's Riemann integrable if on a closed interval a comma b, if this condition holds. But remember, this bounded condition is very important. Okay. We will see what to do for unbounded functions, but the bounded condition is very important. So to compute the integration values, they did the following. So they did the initial thing that we all know now, the equal Riemann sum. How to compute integration in easier way. So they told if a function is bounded just bounded, okay? Then we know it's integrable, of course, because the limit will exist. We can show that. Yes. So the integration exists. You can show that the integration exists, okay? So I need to write this result down actually. Write this result down that no, so we need a bounded condition because bounded functions are always integrable, but Riemann integrable. But if it's bounded on AB, we need that condition. Otherwise, we cannot define integration like that. So if a function is bounded, we can tell that the definition of integration can be computed by dx. Can be computed by the things you know, that limit. See, okay, Sai also asked me why sequence and series are the important criteria. Understand, Sai, that the best way to find the infinite is a set of finite things, right? And the best way is to think about sequence. A sequence means that you are trying to approximate the infinite using the finite. The idea of sequence is that only, and that is the basic, like, but this didn't this was not how it was developed, but this is what they found out. Okay, they found out over the years and they connected, because Archimedes in the BC era was trying to use a sequence to compute the area of under the parabola using rectangles, and he proved, like, he found out geometric series, how geometric series and parabola are connected together. So the idea of human beings, the mind, is that they wanted to approximate the infinite using the finite things. That was the idea. Okay, so they want to find at least an approximate area, and the approximate idea was the idea of epsilon, that they are okay if they just miss by a certain epsilon amount, but if it happens for all epsilon, then we mathematically defined it. Okay, so the infinite is actually beyond human perception. Yet using the finite things we can perceive to approximate the infinite. Okay, that's it. Anyways, coming back to here, we defined it as limit 1 by n. This was the, like, we take the equal length and we this f of a plus b times delta xi, that is b minus a, sorry, not b times, it's b minus a, the delta xi, the length times k, where k is going from 0 to n minus 1. This was the definition. If it's bounded and integrable, you can define it like this, and vice versa. So this was the definition. This makes the computation very easy. Okay, you can compute it because it's a series now. It's a series now, and you know how to compute a series. So they connected integration to series in this way. Okay, computable, both mathematically and in a computer also. So they wanted to compute integration in an easier way. They try to do this. I have taught examples with you, so you just I hope we don't need examples more in this.